Hi, my name is Wang. I work for the technology group in Wolfram Research. Today my talk is about the reinforcement learning in system modeler. Hello everyone, my name is Wang. I work for the technology group in Wolfram Research, and today I would like to talk about some experience when I study reinforcement learning with system modeler. This is the outline for this talk. I shall briefly show the connection between a control system and the reinforcement learning, and then use a system model to create an example and use an existing external implementation to optimize our controller for this system model. So here we have a very basic diagram, which I brought from Wikipedia. We have an environment here, which may be a black box, or also could be something we already know the internal mechanism. And we have an interpreter which probes the system and gets the state and the reward after each step. And we also have an agent which, given under a certain policy, will give the action to the environment. So just for the reference, the reward doesn't need to be positive. It could be negative. And the goal here we want is to find an optimal policy that the agent can take. So after the end of each episode, the reward could be maximized. Many research try different perspectives to describe this loop in different ideas. Many try the Markov decision process, which is definitely correct, but I would just like to show a path from a feedback control system to the reinforcement learning. So this is also a very basic diagram for a feedback control system. We have a plant which can be defined with an ODE in state space. We also have an output function, a controller that can take the output and generate the new input to the plant. This is a very classic feedback control system, and I believe you can find the similarity between these two loops, right? So let's check the details of the Markov decision process, how it's defined. We have, is it too small, sorry. We have a set of the state, we have a set of actions we can take, and we have a discount rate, which you can think about the inflation rate. But we have, compared with the feedback control system, we have two additional things, the probability P and the reward R from state S to the next state S prime under a certain action. So for most control system we learned, well, I learned, given a state and the input, the next state is determined, right? But in the Markov decision process, there's a probability distribution of next state once, even though the current state and the input is given. This making the MDP, the Markov decision process, a superset of the feedback control system. And for the reward in the MDP, we can compare it to the object function in linear quadratic regulator. But the difference is we want to minimize the object function or loss function in LQR, but we want to maximize the reward, the accumulated reward in this process. We are going to use the system model to represent the environment in reinforcement learning. So strictly speaking, the environment only contains the plant, but in most practice, we'll combine the plant and the output function as a combination of the environment and the interpreter. That depends if you want to customize the state and the reward you are going to get. In terms of policy, the agent is going to follow most widely used policy is very simple, the greedy policy. That means when you stand in one state and look at the next possible actions, you will choose action lead to the states that may bring the most reward in the future. So if we know the probability table looks like, we can give each state a value and choose action on the state value function. Similarly, we can have a Q function which maps the tuple of the state and action and to the reward it may bring in the future. With such a Q function, we even don't need to know what the probability table is, which means we can treat the environment as a black box purely. We can choose, we have two functions. We can choose different function to learn, and we can choose different optimization method to learn, whether it's Monte Carlo or it's temporal difference or a combination of both. I have a very simple example here. So the Blackjack game, because the rule may differ from casino to casino, I just refer the Blackjack game in a reinforcement learning book. The ultimate goal is simple. Get larger, you as a player, you want to get the larger score compared with the dealer, but do not exceed 21 points. I implemented with Wolfram language. The major function contains a reset function, which starts a new game. We have an observe function, which checks the dealer's card and the card on the player's hand. We also have an action function, which take an action, and whether it's to draw a new card or to check the current card to see who is the winner. We can use the Monte Carlo policy to we can use Monte Carlo simulation here to run the game like 10,000 times and then draw either a Q function or a V function. The Q function and V function in this game will look like a table. So I just randomly selected several samples from the Q function, Q value set, and the V value set. So if you're familiar with reinforcement learning, I suppose you heard a framework called Zhang from OpenAI. This Python-based framework mainly solves the two problems, provides the benchmark for different reinforcement learning algorithms, and then standardize the function for different environment. So, the research can use this for publications. But yes, this framework requires you to, wrap your implementation into Python language. But I think with the reinforcement learning get more and more matured, many people want to apply this technique to some real questions. For sure, you can rewrite your implementation with Python, but that's not necessary. You can just use system modeler to simulate the plant, because system modeler is a powerful platform. You can create complicated model easily. So in WSM link, which connects the mathematical and system modeler, the real-time simulate function can simulate a model with its simulation time synchronized with the real time. And so I create an invented pendulum as an example here. Let's take a look at the invented pendulum. The model is very simple. We have a cut. We have a pole connected with the frictionless rotation angle, and a ward force is applied to the cut, and the force is the magnitude of the force is defined as the input U. We put two sensors, one to probe the cut position, the other is to probe the angle of the pole between the vertical lines. So now let's check how the model in system model is connected in Mathematica. So let's load it first. So here we define the delta t and other parameters. Similarly, we have a reset function to start each game. The initial condition is randomly generated. We have an observe function which probes the position of the card and the angle of the pole. We have a step function which takes the ward force as an input and simulate the model for the delta t time. We also have a check function, see if the pole has already fallen onto the ground. If it's already onto the ground, we just stop the game. This is display function just for the convolutional neural network, which we will talk a bit later. So we can implement a very simple controller here, like the proportional feedback controller. And it works not bad, to be honest. With a random controller, we have two options, whether going push left and push right. With a random controller, it can simulate for 20 steps. And with this proportional feedback controller, it can simulate roughly by average 50 steps. Well, this is a little exceptional one. But we can still use Monte Carlo simulation to accumulate a large number of samples for either Q function or V function, Q value or V value, and feed it into a predict function in Mathematica or a neural network function you create by yourself. So let's look at that. We define a discount rate and define how the Q value is generated. And we can run 10 episodes. Once we accumulate all the data samples, we can just simply feed the data into a predict function. But I mean, of course, 10 episodes may be a little small, but for the time, just trust here. Now, by default, it uses a random forest to generate multiple decision trees. So a controller can be used once you have the current state and you put all the actions into this predict function and tell which can generate the largest Q value. So you choose that one. Or you can define a neural network function by yourself. This is, well, it is not specific for this problem, but I can still use it. We slightly, format the training data and also put the training data into the neural network function. It's going to take a bit of time. So, because in Mathematica 11.2, we introduced a new functionality called, which allow Mathematica to communicate with external Python or JS node session. So I would like to show how to, if you have already have a reinforcement algorithm and implement somewhere else, how to connect, how to use that existing training scheme for the model in system modeler. We have assumption here. So the Q value for each state tuple equals to the immediate reward plus the discount rate multiplied by the maximized Q value of all next possible state after taking this action. So with this function, if our options is in a finite discrete space, we can index all the actions and create a neural net, create a universal function maps the state to a vector of Q values. So each element in this vector represents the Q value from the state after taking the corresponding actions. The loss function is simple. It's defined as the distance between the left-hand side and the right-hand side. So for the left-hand side, we already know the state is, and we already know which action we are going to take. So we just put the state into the neural network, generate a vector of Q values, and choose accordingly based on the index of the action we are going to take. And for the right-hand side, we know the immediate reward is, we already defined the discount rate, and we just put the next state into the neural network function, and then we get a vector for the Q value for the next state, and we apply a maximizer operator and extract the max value from the output Q value vector. So I implement here, but I don't think I have time to show it. So with this function, you can run the simulation and for multiple times. But each set of multiple episodes is considered as one training for this neural network controller. So you probably need to run even more to get a better performance. And with you can check how many steps it can take from the beginning to the end, and sometimes it will get a maximum, an optimal controller, but it really takes some lucky and to try very many times. Yep, I think that's all my talk today. Any questions?